Welcome to the last day of presentation of this very interesting CECAM workshop on the advances in electrostatic calculations, the road toward exascale. We have been having a remarkable number of interesting presentations at the intersection between the models, the HPC implementations, which have been this quite hard topic, but still fascinating and promising. So the speakers of today will be Dr. Leighton Wilson and Dr. Marcia Fenley. Leighton recently received his PhD in applied mathematics and scientific computing at the University of Michigan, working with Professor Robert Krasny. He is now a principal system engineer at Northrop Grumman Mission Systems in Baltimore. The title of his presentation will be a GPU-accelerated boundary element Poisson-Boltzmann solver. So Leighton, thank you for being here, and the podium is yours.
Thank you so much. Okay, let's make sure that this is shared. And okay, thank you very much, Walter. So everyone can see, correct, in here? Just want to make sure that we're good. Okay. So I'm going to talk about some work that we've done on this GPU Poisson-Boltzmann solver that relates to some other work we've done on fascination methods, including some pretty exciting performance on large systems, which I think is the real highlight of this talk. So first, I'll briefly overview implicit solvation, the Poisson-Boltzmann model, but I don't think any of that is going to be new or surprising to anybody. And I'll talk about the original TABI-PB solver as it stood in 2013. Then I'll talk about a very important piece of this, which are tree code fascination methods, what they are and why we're using them in this context. And then a new fascination method that was really the biggest part of my graduate work, this BLDTT, Beer-Simpson-Lagrange dual tree traversal method, which is a new type of fascination method. Essentially, we took this work and then plugged it into where we needed tree codes in TABI-PB, and we get this BLDTT and GPU accelerated TABI-PB. So I'll talk a little about some implementation details, some performance over our older methods on CPUs and GPUs. And then this last bullet, which I put in red and made a bigger font and underlined and italicized because it's the very important, interesting bullet here. And I think it's maybe by far the most interesting or promising piece of all this. The rest is really background to get to that point. Yes. Okay, so this again is not going to be something that's surprising or news to anyone, but solute-solvent interactions are very important and critical to describe biological function. We need to model this for determining molecular conformation, stable protein states, et cetera. And ions, of course, can be very important as well, because in solvent, they can screen electrostatic effects, impact coordination and binding, et cetera. So the model of interest for us, and I guess both the talks today actually are about Poisson-Boltzmann equation. I'll hazard again, I'm talking about computational aspects for most of this talk and not the some of the interesting physical aspects like Marcia is. But the Poisson-Boltzmann equation is our model for solvation for the work in this talk. So you can imagine that you have some biomolecule represented by a bunch of hard sphere atoms. You put point charges at the center of those atoms, and you have some boundary that separates your solute environment from the surrounding solvent. And then you might have some dissolved ions around it as well. Oops. There we go. So this right here, this green is our solute environment, our omega-1 environment. So the electrostatic potential inside the solute, inside our boundary gamma, is simply represented by a Poisson equation, with some dielectric constant. And of course, our charge density is nothing more than the sum of these point charges. So yes, so in the outside environment, we have, there we go. In the outside environment, we have a Helmholtz equation from the electrostatic screening of these ions. So we have this screening term here in this environment. And of course, if we had no ions, this would just turn into a Laplace equation. So we have a discontinuity across this boundary related to the dielectric constant. And we also have inside this environment, charge density determined by our point charges, and outside outside the boundary, we have the screening term from our ionic concentration. So the quantity of interest which we're using to benchmark most of our results at the end of this talk is the solvation energy, where essentially we're measuring the change in the free energy between this vacuum state where our biomolecule is just sitting in a vacuum versus the solvated state when it's actually in solvent. And this is a function of our reaction field potential, the difference in potential between the vacuum and solvated states. So how we compute this quantity actually becomes very important at the end in a way that we never quite expected it to be. You'll see when we get there. So Jufer back in '91 created this boundary integral form of the Poisson-Boltzmann equation, where we have these two integrals over the boundary that are based on these integral kernels, and these integral kernels here are nothing but functions of our Coulomb and screened Coulomb kernels and their normal derivatives. So notice that when we solve this coupled integral equation, we get both the electrostatic potential along that boundary gamma, and we get its normal derivative. These source terms here, and this is another piece that ends up becoming much more important, how we calculate it, than we ever expected it would, are functions of all of the charges of our atomic positions, evaluated with these kernels, with the Coulomb kernel and the screen Coulomb kernel for these two source terms here. So when we discretize this, of course, we end up getting a boundary element method. So we have to discretize this surface gamma to some sort of triangulated surface, and then we end up with a linear system, and that produces our boundary element method. So the 2013 tree-code accelerated Poisson-Boltzmann equation solver, TABI-PB, that Gang and Krasny developed, used MSMS to generate this molecular surface mesh from the solvent excluded surface, and used centroid collocation to generate the linear system. So essentially what this means is that at each one of these little triangle elements here, put a point at the middle of the element. And that is the point that represents your element. Well, when you do this, of course, you end up with this dense linear system. And GMRes still is used to solve that resulting linear system. But inside GMRes, you have these matrix vector products. So if you take this and write this in its discretized form, you essentially have matrix vector products where you put in some value for the potential and its normal derivative, and you calculate, and you use that to iterate, with an iterative solver like GMRes. So you end up with something that's dense, because every single one of these little elements, so these are like our centroid collocation dots. Y'all can see my pointer, correct? Hopefully.
Yes.
Okay, good. Yes. So each one of these dots, which are like the centroid, collocation representation of our mesh, each of these elements is going to have to interact with every single one of the other elements. So if you have n elements, that's O of n squared operations to do that matrix vector product. So tree codes were used to speed this up from being O of n squared operations to O of n log n operations. The tree codes used in the original PB were based on these Taylor expansions, which I will not talk about today, but it was the method by which those approximations were done. So now I'm going to spend briefly some time overviewing tree codes before I get into what we're doing now. So the core idea of tree codes and fascination methods is essentially finding ways to solve the n-body problem faster. So we have n particles interacting under a long-range potential. Of course, we have what I just showed previously, like our little surface mesh, where we have each one of these n particles interacting under some potential with these other n particles representing the surface of our biomolecule. But we can have other setups as well, right? I mean, our source particles that induce a potential and the points at which we evaluate the potential don't have to be the same. And this also becomes very important later, you'll see. So in this case, we have these source particles and we have these red X's along the grid. And this also is an n-body problem that we can speed up with tree codes. So we don't have to do, for each one of these source particles, compute something at every single grid point. So we'll use this as a little setup to kind of dive into these methods a little bit. You can imagine, again, your source particles and target particles don't have to be the same. They are the same over here, but they don't have to be the same. So we'll just take a little collection of particles to talk about how we actually approximate these interactions, speed it up. So we can imagine we have this little collection of source particles, these little black particles, and this little collection of target particles. So these induce the potential, and these are the positions that we want to evaluate it at. If you have n targets and sources, again, that's O of n squared operations. Every single one of these black particles has to interact with every single one of these blue positions. So the tree code idea essentially allows us to replace this little cluster of source particles here with a fictitious particle with some sort of approximation. And now this fictitious particle interacts with all of these blue target positions. And we group our particles in such a smart way that we end up with O of n log n operations. So how do we actually cluster our particles? Well, we have to build some hierarchical tree on all of our particles forming nested clusters. So I'll show an example here just to get the idea across, where we have, this is 100 particles sitting in space, and we'll just keep bisecting it until there are no more than 4 particles in clusters at the bottom of our tree. So first we have the level 0 node in our tree. This is the root. It contains all the particles. We bisect. We keep bisecting. Here's our level 3 bisection. Notice that a few of these didn't get bisected on level 3 because they already had only 4 particles. There's no reason to keep bisecting it. And we bisect a little more, right? There are a few of these that we still had to bisect down at level 4. All of the nodes without children we call leaves. And notice, of course, that leaves can occur at any level of the tree, right? So here's a level 1 leaf, here's a level 2 leaf, here level 3 leaves. Okay, so we have some way to cluster our particles. Well, we have to determine when we actually interact with a cluster approximately or not. So we need some criterion for well-separatedness. So you can imagine here, this xi is our target particle, and this is some cluster of source particles y right here. We have some distance, big R, between the center of this cluster and this target particle. We have some radius of this cluster. So typically when we build these clusters, what we'll actually do is we will shrink the cluster boundaries to just contain the particles. So we really make this radius as minimal as possible. But that's our little r. And then we have to have some sort of parameter, this multipole acceptance criterion or opening criterion, to determine if we feel like this is well separated enough to interact with approximately. So if theta is bigger than big R over little r, then this is far enough apart. And so we can evaluate this particle cluster interaction approximately. If it's less than it, and that cluster is not a leaf, so there exist more clusters below it, then we would open the cluster further and we would take a look at the children clusters. And if it is a leaf, well, the MAC criterion has failed. There's no further we can go down to the tree, so we just have to evaluate that interaction directly. So I'll show you what one of these tree traversals looks like real quick. So here's our group of 100 particles again. Here's the little tree of nested clusters we built on it. We'll take this right here as our target particle, and we'll just go through the traversal. The first level traversal with the root, assume that's done. So we first look at this big cluster up here. Well, we decide this one's far enough away. This is well separated, so we can accept this interaction. So this blue particle will interact with this entire cluster of particles here only approximately. This one's also well separated enough, so it's fine. This one, however, we're too close, so we have to traverse further. So now we go down a level to the second level. This cluster here is far enough away, we accept it. This one right here is far enough away, we accept it. This one's too close, traverse further. These two little red ones are well separated enough. This one only has a single particle in it, so there's no reason to approximate it. We just interact with it directly. This one's too close, traverse further. This is a well separated interaction, accept it. There's not enough particles in these, so we'll just interact with them directly. When we go through this whole procedure, what you see is we end up with 16 approximate interactions with clusters and 15 direct particle interactions. If we had just interacted with everything directly, that would have been 100 interactions with no approximation. So, we do significantly decrease the number of operations that we have to do. Of course, we have to actually have a way to approximate these interactions. So I've told you how we determine what to approximate, but we actually have to approximate them. So we have our targets xi, our sources yj, and with each source associated charge qj. Then the potential that we get at our target position xi is, of course, the sum of kernel evaluations between the target and the source and the charge of the source. The common kernels for this kernel that are important to us, as you saw at the very beginning with the Poisson-Boltzmann equation, are the Coulomb and the Yukawa or screen Coulomb kernels. The key idea for approximating this is that we need to approximate it with a sum of separable functions. So if we can take this g of x comma y and turn it into a sum of functions of x times functions of y, then we can start actually making some progress with our approximation. So for a given cluster of target particles, we will represent for a given cluster of source particles, we'll represent the potential at a target x due to that source cluster with this phi of xi comma c. And of course, this is just the sum of all the source particles in our cluster where we're evaluating this kernel interaction here times those source charges. A very simple way to approximate it would be to simply take all of your source particles in that cluster and replace them with one fictitious particle at the center of the cluster and make the charge of that fictitious particle just equal to the sum of all the charges in that cluster. And that's what we're doing here, right? So we replace this sum here, or we replace this sum here with this evaluation of the kernel at the target xi and the center of our cluster yc times this moment of c. In this moment, this is just the sum of all of our source charges. So you'll notice, right, this takes our separable form. So this function of x here, the function of our target position, is the g of xi comma yc. And the function of our source positions is just this moment right here, because this is just the sum of all of our source charges. So this is one really simple approximation. And in the little diagrams I showed, this is kind of what I was showing you, right? I just put a fictitious particle at the center of a cluster when I want to interact with it approximately. So put all these pieces together, gives you a particle cluster tree code. Everything else that we do is based on modifying this idea. So what does this traversal actually look like? Well, first we have to pre-compute all of our cluster moments for all of our clusters. And then for each target particle, we do our tree traversal, starting at the root of the tree. So if our target J is well separated from C, or from that, from this cluster C, when we first start traversing, it'll be the root. Then we can update the potential with the approximate interaction between J and the cluster C. If it's not well separated from C and that cluster C has no children, then we have to update the potential with a direct interaction. And if that cluster C has children, then for each child, we do this, we recursively traverse this function. So importantly, if we have M targets and N sources, the tree is built on the sources. So, assuming certain conditions of how the particles are distributed, this tree has O of log N levels. And at each level of the tree, each source contributes to one cluster moment. So that's O of N log N operations to compute our cluster moments. When we actually compute the potential, the tree is descended a total of M times. So that's O of M log N operations. So this gives us a total operation count of O of N plus N log N. Well, there's a lot more you can do with this idea. What I showed you, we were just clustering up the source particles here, but why not cluster up the target particles as well? And this is essentially the idea behind FMM or cluster-cluster fast summation methods, and we kind of ran with applying this idea to some of the tree code methods that we were working on. So in this case, you can imagine taking this group of particles again. So in this case, these are the same set of particles, but we can treat them as two trees, right? We already have this tree built on our sources. Well, we also have a tree on our targets. It's the same set of particles in this case. And now we can do a tree traversal where we traverse both this target tree and this source tree simultaneously. Well, if we do this, our criterion for well-separated changes, right? Because we have both a source cluster and a target cluster. We still have this cluster distance R here. We have a target cluster radius and a source cluster radius and some opening criterion. So, the idea we played with here is well, okay, in this case then, when we want to evaluate this interaction approximately, right, it just means these are far enough apart. If these are too close, then we have to open one of the clusters further, and one of them is not a leaf. If both clusters are leaves, then we have to evaluate the interaction directly. So, the question then is, okay, well, how do you determine which cluster to open? And roughly, you can just keep going back and forth between opening up a target cluster, and then on your next traversal through, you open up a source cluster. And then you can build up a list of well-separated clusters that you want to interact approximately. So the other big idea, other than applying this to our tree codes, was a new way to approximate these interactions besides what we've done previously with Taylor tree codes, or just the simple example I showed you with those moments of fictitious particles in the center. And something that Robert had done a lot of work on was this barycentric Lagrange interpolation. So now this is the method that we end up using to approximate cluster-cluster interactions. So brief overview of barycentric Lagrange interpolation. If you have some function f of x that's defined on an interval, and you have some interpolation points, sk. Then you get the following for your interpolating polynomial of f, and the following are your Lagrange polynomials. Importantly, if you choose these interpolation points to be Chebyshev points, then these weights right here become distributed along O of 1, right? So they're just -1, 1/2, -1/2, 1, which ends up being really nice because it means that you have this stable and very easy to compute polynomial interpolation. So we ended up running with this idea for approximating our interactions. So I'll show you what this looks like for approximating a particle cluster interaction. Return this idea of a potential at a target due to this cluster C. This is the same equation I showed earlier. So we expand this kernel function. This is what we'll interpolate, and we will interpolate it about Yj. So then we end up with the following expansion in terms of our Lagrange polynomials. Well, importantly, what you notice, yet again, we can get a separable form here. This right here, these are our functions of x of the target position, and these are our functions of the source position, y. And again, these are multiplicative, right? So these are separable. So we have a sum of separable functions. So when you do this grouping here, I rearrange my signs a little bit. So here's the full, particle cluster potential. This right here, this value right here, we call our modified. This value right here. So you have to flip these. I should have added another step here to show this. Flip these two sums, and you end up with these modified charges here. And one thing to notice about this form is that the direct potential form, looks as follows, right? We have our evaluation of the kernel times these source charges, and when we approximate it using this barycentric Lagrange interpolation, we get something very similar, except now instead of summing over the source positions in the cluster, we're summing over some interpolation points in the cluster. And our charges are now these modified charges. So you can kind of see why we call them the modified charges. The fact that these look so similar ends up being very, very important for us, that these both take a very similar form, where even after we do this interpolation, this approximation, it looks a lot like a direct sum. So I wanted to elide some of the details of our dual tree traversal, but importantly, you can make some smart decisions with your algorithm where adaptively, depending on where you are in the tree and how many particles you have in a cluster, you really have 4 choices of interaction between a target cluster and a source cluster. You can interact directly, particle-particle. You can approximate. You can use our interpolation just on the source cluster. So here you actually see where I've replaced all these particles in here with the interpolation points. So essentially, this is now, in some sense, a particle-particle interaction between these target positions and these interpolation points. Well, you can also do a cluster particle. We have all the pieces to do it now. So you can also interpolate your target cluster instead, and not your source cluster. Or you can interpolate on both, and you end up with this cluster-cluster interaction, where both of them are being treated approximately at these interpolation points. So you have a set of interpolation points in your target cluster interacting with a set of interpolation points in your source cluster. So there's a lot of freedom of what you can do. There's a lot of flexibility for determining how things interact. So with all these pieces put together, and this is really the biggest part of my graduate work, was we built this library for fast summation of in-body interactions called Berry Tree that implemented the BLDTT using barycentric Lagrange interpolation. One really nice thing about the fact that our approximations take this direct sum form, and I'll show this on the next slide, it ends up being very easy to map to a GPU. So we built something that had this O of n traversal instead of this O of n log n traversal, and we could easily map it onto the GPUs. We also did, I think, some pretty cool things with MPI that I'm not going to talk about at all. But we were able to do some pretty large runs. We took this in-body interaction library that we built, and we ran it on the Ascent machine, which is a test bed of Summit at Oak Ridge, and used up to 24 V100s. On the old SDSC Comet machine, we ran it on 32 P100s. And just yesterday, I ran it on a large number of the new V100s on their Expanse machine. So we can get pretty large and do some pretty cool things with this library. So of course, now getting back to the real focus of this talk, the most important application of this, of course, is using all the ideas in Berry Tree and applying it to the Poisson-Boltzmann solver, to TOBEPB. And I'll get to that in just a second, but I want to note quickly why this is so easy to implement on a GPU. So you can imagine here, this is our set of target particles. This is our set of source particles. On a GPU, you have these two levels of parallelism, right? You have these blocks of threads, which is one level of parallelism. And then within each thread block, you have all these individual threads that have some shared piece of memory. So essentially what you can do is each one of these targets can be assigned roughly to a thread block. And then each one of these source particles can be a thread on this thread block. So you end up having this really nice and easy mapping to GPU parallelism with interactions like this. And of course, because this takes the form really of a direct interaction, so this is the particle cluster interaction. It takes the form of a direct interaction. We've just replaced these particles with these interpolation points. We can do the exact same mapping, right? So everything that's nice about doing the direct sum on the GPU, taking advantage of these two levels of parallelism, we can do with our approximations as well. And this is what makes it so good for GPUs. So putting all these pieces together, back to TOBEPB. We recently built a new version, learning from everything we learned with Berry Tree with regard to these fascination methods. And we don't really have a name for it yet other than TOBEPB. So I've taken to just calling it BLDTT plus GPU TOBEPB. We use NanoShaper instead of MSMS, the generative linear system. Thank you, Walter, because this, we actually have a paper comparing these, and NanoShaper makes a very big difference for us. Instead of using centroid collocation, we use node patch. The next slide, I'm just going to very quickly touch on that. We use BLDTT and a lot of the ideas in Berry Tree for calculating these matrix vector products in GMRes. So we currently only have single GPU support. And we also have multi-core CPU support with OpenMP because it's an easy free win to do that. Quick note about the node patch method. With the centroid collocation, I said that we placed for each of our surface elements, we placed a particle at the center of these triangles, at the centroids. And these were the positions that formed our linear system. The node patch method, you can instead place a particle at the vertices here, and then the area of the face, quote unquote, that it's associated with is 1/3, the sum of 1/3 the area of all of the surrounding mesh elements that meet at that vertex. So this node patch method actually has quite a big impact on decreasing the size of our linear system without giving up anything in terms of accuracy, which is very important for us. So now I want to actually show you some results about putting all these pieces together. So these first few results I'm running on this protein with PDB ID 1863. It's not very big, about 2,000 atoms. I've got 3 lines on these graphs, so let me explain briefly. This black line is the original, more or less the original 2013 version of TOBI-PB. And so in this case, we're using a Taylor tree code for doing our matrix vector product, and we're using centroid collocation. The red line, we're using the Taylor tree code, but we're using node patch instead of the centroid collocation. And then the blue line here, we're actually using the full BLDTT, all the work that was done for berry tree with node patch to do that matrix vector product. I'll make a note on the parameters here. You know, the parameters for the BLDTT are naturally a little different than the Taylor tree code, because there are different considerations of what optimal parameters are. But you know, these are parameters that are comparable between the two. So this is a fair comparison. So what we're calculating here, this solvation energy relative error, we're essentially, we had some reference that we took from doing a direct sum calculation at a very high mesh density, and we use that as our reference. You know, what you'll notice here on this solvation energy relative error versus time, so this is increasing mesh density, so increasing the nanoshaper density of the mesh. You know, we had this huge jump just from going from the centroid collocation to the node patch with the Taylor tree code version. And the jump here from the Taylor tree code node patch to the BLDTT node patch doesn't look quite as extreme, other than you'll notice that the slope of this line is a lot lower. In fact, you can see that these lines have an n log n slope, and this line has a slope corresponding to O of n. So replacing the Taylor tree code with the BLDTT, we go from O of n log n for our matrix vector approximation to O of n. So I like this graph too, because it just shows you, just in terms of the number of elements in along our surface, how much cheaper is it for us? And it's quite a bit cheaper. You know, overall, when you take into account solvation energy relative error as well, doing node patch with BLDTT, roughly a 10 times improvement in efficiency over what we were previously doing with TOBI-PB. Now, you know, the real great benefit of using the BLDTT here and all the work on berry tree is that we can do it on GPUs. So this in and of itself is not a super fair comparison for the CPU, but it shows you that it works on GPUs and we actually get decent speedups. So we have here, for this exact same problem, taking this blue line here, we have it on both the CPU, running it on a single CPU core, 2.5 gigahertz Intel Xeon. It's gold, so it's a good CPU, but it's just a single core. Comparing it to a GPU run on an NVIDIA P100, you know, 30x improvement over a single core CPU. You know, people can quibble whether this is a fair comparison, and it really isn't, but it shows you that we can speed up significantly actually using a GPU, that we can take advantage of the GPU. One thing I will note here, that you notice we have a solid line and a dashed line. The reason I have a solid and a dashed here is because, so these dashed lines include the service meshing time, the calls to nanoshaper. Doing a nanoshaper on the GPU would be very cool. And I've dug a little bit into nanoshaper's code and thought about how that might be done. So that includes that.
Working on it.
Awesome. Yes, that would be very cool. And would be a great addition to this, and would help us out considerably. So these solid lines here, we're just excluding that service meshing time. So I'm showing here a breakdown of the components of our code, the runtime on the CPU versus the runtime on the GPU. The red box parts right here is everything that goes into the matrix vector product. So on the CPU, right, here's our build mesh time. So this is like the calls to nanoshaper. These orange parts are computing those source terms. like I said, this red box is the actual matrix vector product. This blue part is at the end computing the solvation energy, and this red part is other operations. So we put it on the GPU, right? There are other things that start to dominate what takes a lot of time. Down at a scaling parameter, a nanosheet scaling parameter of 1, we're really spending barely any time doing our actual matrix vector compute. We have a lot of this other compute here, and we're more dominated by just the time to build the mesh on the CPU. Now, one thing that you'll notice about this, I made reference earlier to computing the source terms and computing salvation energy. What I showed you so far, and for a long time, we were only concerned with this piece, right? We have this matrix vector product we have to do to solve this GM-res linear system. We want to turn this O of n squared into O of n. These pieces, computing the source terms, computing the salvation energy, are O of n times n sub c, where again, n is the surface elements and n sub c is the number of atoms. This was always so small that we never even really considered or thought about these terms, or if we would need to speed them up in any way. But the interesting thing about running bigger and bigger problems is you always end up finding computational decisions, algorithmic decisions that maybe you never really would have considered otherwise. And so that's what happened to us. So we tried to up our game a little bit and actually start running some big things for the first time with this new TABI. So we ran on this Zika virus. I think Chris Cooper was on the call. This paper, which Chris Cooper was worked on, was a big inspiration for this, because we saw what they did with this large structure. This is 1.6 million atoms. So in this case, we couldn't have even attempted to run this on a single CPU core. We could have used OpenMP and run it on mini cores, but this is a good opportunity to try to show what we could do on a GPU. And we got results. So we ran on nanosheet per scale from 1 to 2. We got results that are very comparable to what Wang and Cooper et al. Reported in this paper. We were pretty happy with our total time. How long it took us to actually do this computation. But we quickly noticed that the time actually spent doing the GM-res, the time spent doing that matrix vector product, was really a pretty small fraction of our total time, which is something that we had just never worked on systems of a size where this kind of thing crept up before. Well, the reason was because we finally found the problem, right? We've got 1.6 million atoms. We've got, so using the node patch, the number of computational elements we have are the vertices. So we're using 5 million to 20 million vertices. These O of n times n sub c pieces finally mattered. So this orange piece are the source terms, and this little light blue piece, the salvation energy, these finally mattered. We weren't spending all of our time doing this matrix vector product, the GM-res iteration. We were spending all of our time on these source terms and computing the salvation energy. Well, there's no reason we can't take everything we did with the BLDTT and the matrix vector products. There's no reason we can't apply the exact same ideas to computing the salvation energy and computing the source term. And in fact, that's exactly what we end up doing. So importantly, and this was the reason I made sure to include on that little intro slide about the in-body problems, right? Your source and target particles don't have to be the same. So in this case, this the linear system, the GM-res, they are the same. The source and the target particles are the computational elements. With the source terms here, we have as our source particles the atoms, but we have as our target particles the computational elements. The salvation energy, if you want to use some sort of fascination method to accelerate this sum. You can make either choice, because at the end you'll have to do a reduce where you sum your whole array and you get, you know, one final salvation energy sum. So you can make either choice, and we end up making the same choice we do for the source terms. So we treat the atoms as our source particles and the elements as our targets. But the upshot is we can use the BLDTT on these pieces as well. There's no reason we can't. Well, we do that. And the few things that, before I show you the pretty graphs related to it, just a few things I want to point out from this table, right? The GMRes time is still the same. I mean, you know, within the noise of the system we're running on, but we've greatly decreased our total time because we finally handled these other pieces, you know, more than half, in some cases, you know, a third, with minimal increase in our memory footprint for, you know, storing related quantities for our two new BLDTTs for those pieces of the code. So for all of these, and I made a point here, I should have pointed it out. So we're using a GMRes tolerance of 1e minus 4.001. So that's kind of our benchmark for accuracy for these. So the change in salvation energy for when we approximate these other pieces with a fast summation method was within our GMRes tolerance. So, you know, we didn't introduce any more error than was already present based on our GMRes tolerance. So now you can actually see on these little graphs the difference it made, right? So this big orange piece and this big light blue piece have shrunk considerably. And now we're back to really being dominated by the matrix vector product piece. And if you look at this in terms of the total time instead of as a percent breakdown of the time, you can see just how much we reduced our total compute time. So again, a third to a half from what we first did. Well, you know, we decided we wanted to go a little bigger as well. And this H1N1 structure from an Amar paper, this was actually provided by Walter. So thank you, Walter. We ran on this as well. It's kind of a pretty picture where we actually show the induced surface potential that we got from TAB-UPV on this molecule in the same physical environment that we did the Zika virus on. We see the exact same kind of thing, right? Here it was even more extreme. So in this case, when we first ran it, using a Nash-Over scale of 0.5, so there's 14 million atoms of this, but we had 12 million vertices for Nash-Over scale of 0.5. So we actually had more atoms than we did, you know, computational mesh elements. And so in that case, when we ran it without having with our BLDTT, just the matrix vector product, again, these guys were huge pieces of the runtime. This piece was our actual matrix vector GMRes compute, and you know, applying the BLDTT in these places made a huge difference. Greatly shrunk these pieces, and you know, we decreased the total time to you know, well less than a 10th of what we did, more like a 20th of what we were doing when we just used the matrix vector product. We just used the BLDTT for the matrix vector product. So, you know, it was an interesting case of we finally start running on these big structures, and all of a sudden these pieces of our code that we'd never really considered, suddenly we have to do some smart fast summation things there as well. And this BLDTT method is so flexible that we can do it on all these different pieces of our code and get some really good speed ups from it. So we ended up being able to do this really large structure in, you know, about 1700 seconds total. So this is where, yes, forgot to, this other piece here, you notice this big red other piece shrunk as well. This actually includes computing the Coulomb energy, which there are enough atoms that suddenly, you know, as just a quantity that we want to present, we were computing the Coulomb energy as well of the structure. And so this also we applied the BLDTT to. Why not? And you So that's where everything stands at the moment with our code and the kind of structures that we've done. Here's the GitHub link to TABI-PB and the GitHub link to the berry tree fascination package that all this is based on. I very much would encourage you to take a look at it if you're interested in it. One thing which I did not talk about at all here, but I'm really interested in doing towards the future, with berry tree, we've already figured out a lot about how to smartly do a distributed memory implementation. So I mentioned that we have results where we're running on like 32 pretty powerful GPUs. There's no reason we can't do the same thing with TABI-PB. And the thing is, some of the design considerations are different, the ones we made in berry tree. So I'm still thinking about how best to do this, but very much we would like to also make this MPI parallelized and have the same, 2 levels of parallelism. One at the node level, and then one at the GPU level on a given compute node. And then we can keep pushing that and hopefully, start running certainly not quite exascale, but we're definitely thinking about how can we run this efficiently on bigger and bigger systems. So we also have this version of TABI-PB as a submodule of the adaptive Poisson-Boltzmann solver package out of Pacific Northwest National Lab. Some quick acknowledgements of people who were a big part of this work. Robert, of course. Nathan, who was in my same cohort in graduate school, another student of Robert's, who's now at Los Alamos. We worked a lot in berry tree together. Wei Wah, of course, who had a big impact and a big role in TABI-PB, and Nathan Baker, Pacific Northwest National Lab, who has helped get us a lot of exposure by way of inclusion in APBS. So yes, so that is the end of what I have. I would be more than happy to take any questions.
Okay, thanks a lot, Leighton. This was very interesting and nice. Before I already see some question from Christopher.
Hi, Christopher.
Hey, how you doing? Great.
How are you doing?
That's impressive work. Thanks so much. Really enjoyed it. And thanks for mentioning that work. Unfortunately, it's still not published. We're fighting with reviewers yet, but it's still to see the light. Before I have to go to teach like in 2 minutes, but I was interested in, did you compare at some point, and this is something that I had a lot of trouble with, where's the crossover point with just a regular n-squared implementation on a GPU?
Yes, so based on our, the problem with this question is that, well, no, I guess I'm more to the CPU side. So with berry tree, we looked quite a bit at with berry tree, and roughly, at least given our direct sum implementation, it was, if the sources and targets are the same, I think it was around 50 to 100,000 particles per berry tree. The problem though, and the reason that I don't want to, is that people can do very, very smart things with a direct sum implementation. Yeah. And the berry tree direct sum implementation was, was pretty, that we were comparing to was pretty dumb. It was pretty simple. Like, we got rid of the 1/2 that when we had our sources and targets are the same, we at least got rid of the half factor from, a source and target interacting versus that as a target and that as a source interacting, that 1/2 factor. But people can do such smart things with implementing that on a GPU that I'm not sure where the crossover point would be for a really smart direct sum implementation on a GPU.
But 50,000 of 100,000 seems reasonable. When I tried this with the GPU, I got over to like 200 or 300,000. So that that seems reasonable. That's cool. And thanks a lot for this, because it actually, for example, that work that you're mentioning, we had to compare with an old code of mine that used a very more naive implementation that used a lot more iterations. So our comparison was not very fair. So this allows us to have something to look up for comparison. So I'm really looking forward to trying it out.
Yes, and thank you for your work in that paper, because it definitely gave us a lot of inspiration about sort of trying things that we hadn't tried before in terms of size of systems. So yeah, if you want to connect about any of this, please reach out.
Yeah, really nice. Thanks, and great to see you.
Yeah, good to see you too.
Yeah, sorry, I have to go teach, so probably I have to sneak out.
I actually have a meeting.
Okay. Before I see any other questions, I have one myself. Do you, when you move from particle-particle to particle cluster and then to cluster-cluster interaction, do you have an estimate of how much accuracy do you lose? Do you have some parameter characterizing your approximation?
Yeah, so this is another really good question. We've talked a little bit about good ways to rigorously estimate it. We don't really have any at the moment. I mean, there should be a way to do it, right? I mean, the polynomial interpolation is pretty well characterized. At the moment, the best we're able to do on that front is simply comparing what we do, or comparing our results to what happens if you do it as a direct sum. That's currently the best we have at the moment, but it would be very nice to actually have something that rigorously tells us a little more. So the short answer is no, but I would like to have that.
Okay. Are there any more questions? If not, let me thank again the first speaker of today, Leighton. That was a very nice presentation. Thanks a lot.
Yes, thank you very much.